Our first presentation is about next generation elastomer for SLT ATE evaluation. Our presenter today is Mike Dell, and he's an expert in electromechanical interface solutions. Applying his degree from Cal Poly SLO in mechanical engineering, he started his journey in semiconductor test as a change kit and handler applications engineer. He then proceeded with roles focused on test cell integration and tester interface design. Next, after gaining the expertise from the tester side as a Tier 1 GAM for Kulicke and Stofa, he focused on the device interface. Now, after 15 years with ISE, Mike works with key customers to support some of the industry's most challenging test applications. So, thank you, and please start your presentation.
Okay, thank you, Mark, and thank you, Ira and the TestCon team for putting this together. It's an interesting format. First time ISC has presented here in the US event, and it's nice to be part of this, so thank you. My team in Korea, SH Joe, JH Yang, and Donghyun Woo, they put this presentation together. They spent a lot of time working through our different studies we've done for some of our larger customers. We typically do a lot of qualification work at our headquarters in Seoul, Korea, and you'll see a lot of those reports as we go through this study. But what we want to talk to you about today is our elastomer technology and some of the lessons we've learned in the last 20 years or so on ways to advance it and make it more suitable for ATE and SLT testing. So with that, we'll go through. We'll talk about recent trends, some of the key factors that cause elastomers to fail early in their life, what we're doing with reconfiguring our elastomers, building them as a more advanced product so they can hold up to the larger devices with high warpage, devices that go through a lot of power cycles, and these demands for automated tests where we want to see elastomers maybe not last as long as a traditional Pogo pin, but at least approach that kind of longevity. Okay, if there's any questions as we go through this, like Mark said, and Ira pointed out, please jump in and ask questions because it's great to talk about while we're looking at some of the images and reports. Okay, the reason I think elastomers have become such a good product as we move into these more advanced areas of testing is because our industry is moving to finer pitches and the speed and signal requirements are going up every year. So this is a big, compelling reason why ISC has continued to evolve the elastomer and develop some great relationships with key customers to make these elastomers suitable for all kinds of testing, including the automated testing. Okay, so you've seen this throughout this conference. As we've gone from 3G, 4G, 5G, and whatever's coming next, the speed of test is rapidly expanding beyond what you can do with a traditional Pogo pin. So for us, the ISC elastomer has had the speed capability for as long as we've been building elastomers, 20 plus years, but now the industry is kind of catching up to that need. So there's a lot of momentum to switch test processes over to use elastomers, right? So from DRAM to GPUs to CPUs, ISC is seeing more and more of our customer base talking to us about how to enable elastomers into the automated test environment. But basically talking about how the industry, the speed requirements, the test requirements, everything is giving ISC and our peers in the industry that do elastomers, there's a lot of motivation to switch to these more advanced technologies. Okay. So you can see this slide, I hope. The industry, probably as long as I've been working with ISC, Pogo pins have been the workhorse when you get to ATE and SLT testing especially. Our elastomers have done well in the labs for 20 years, because they're almost like soldering a part down. But when it goes to automated test, everyone requires a little bit more compliance to make the automated test setup easier, the serviceability, and the long life, right? So for Pogo pins, the evolution has been to go to more of a coaxial solution or a very short contact solution. And the Pogo pins, some of the ones we've seen at TestCon, are getting very, very short, which is great. We build those as well. But for us, the goal ISC has is how do we evolve our elastomer to make it a good comparison technology to work in these ATE and SLT applications, right? So for us, the image on the left here, we're looking at what we would consider our standard elastomer. We call it SILMAT. You have thousands of metal particles suspended in silicon rubber. The silicon rubber gives you the compliance. Squeezing those metal particles together gives you the good signal path, right? And what we have on the left there is probably anywhere from 0.5 millimeter to 2 millimeters tall, depending on how we construct it. And we have thousands of different recipes for how we do that. When you look at this, the reason the elastomer fails is that high force distribution at the contact point, especially with the BGA device, right? You can see what we're showing here for the strain with the red is how the force is loaded right at that point where the ball intersects the elastomer at the top surface. So that leads to more contamination. It also leads to a breakdown of the elastomer at the top. So we're going to work on ways to improve that. Okay. This is showing a little bit more detail. That top view is probably the key indicator. You can see a lot of solder migration from the solder ball. You can also see maybe a void where some of the gold powder has either been pushed down into the body of the elastomer or been dislodged from the elastomer, which doesn't happen much, but it does happen at some level, right? So what we want to do is come up with ways we can improve that. Okay, so what we've done here, this is an elastomer we've been working with, this kind of construction for a few years, where we intentionally create some different zones in the elastomer. And what we're trying to do is get the elastomer to go through more of its compression cycle down inside the body of the elastomer. We want to minimize the movement at the top of the elastomer and move it down into the body. That's going to help us keep contamination minimized. It's also going to help us alleviate the stress of the elastomer, because one thing that causes it to fail is the silicon rubber holding the elastomer. As it expands, it starts to tear. And it's that micro tearing that causes the elastomer to kind of lose its bounce back. It won't have enough force pushing back on the solder ball or the pad or the lead to give it reliable contact resistance. Okay, so we're going to look at how we do this and how we can get that force to move lower into the elastomer. Okay, on this is a more advanced slide. So as I go back here, this was when you look at the failure on this. This is the top pad of the elastomer, right? You can see the damage on that top zone. When we move forward and we use our newer elastomer type, this is after probably 100,000 insertions is what we normally do our testing to. And you can see the difference here. That top pad is still in remarkably good condition. And we've done that because we are causing the elastomer to bulge out more in the body of the elastomer, not at that top surface. So the key thing there is this air pocket, the void area that we've created internally in the elastomer. That allows this column, as you compress it down in the z-axis, to bulge out more in the middle in a controlled way. It eliminates the micro tearing, and it eliminates the need to have so much movement at the top surface of the elastomer, right? So we can get that force distributed down through the body of the elastomer. We can help eliminate some of the contamination issues because there's not as much movement. So there's not the side action scrub is minimized, where we're not going to be pulling debris off of the device as quickly, right? And then also some of the things we've advanced is, we can make this column denser, that's more metal, less silicon rubber inside the column by giving these air pockets. That helps us with lower resistance, higher current carrying capacity, optimized for better speed, right? Okay, this is looking at, again, our standard Stomat elastomer. You can see no air pockets, no cavities. So this elastomer, as you squeeze it down, the silicon rubber is basically an incompressible fluid. It has to move, right, to give you that compliance. While it's moving with nowhere to go, that's where the micro tearing happens. And you get more of the stroke coming right off the top of the elastomer, which causes this high stress. When we move to our newer types, we've created the air pocket, which is going to allow this expansion to happen internal to the elastomer in a controlled way, preventing the micro tearing and minimizing the contamination. So we've got 3 videos our R&D team put together here. So I'll play these for you. This is kind of showing how the stress happens as the BGA device engages with the elastomer, right? And the key thing is our standard elastomer is how much stress concentration we have right under the solder ball. Remember that, because once I start these other animations, this image goes back to its native state. So, oh, it actually stayed, which is great. Oops, that one again. Okay, so we're trying to minimize the stress. You can see a lot of movement happening in the body of the elastomer. You know, very little stress right at the solder ball point. The difference with these 2 types is an optimized column size. The construction's the same. We're just changing the diameter and the metal density of the contact and the height to tune the elastomer to give electrical signal performance. So same kind of construction with the air pockets. Okay, so when we do this, we're eliminating that high stress point. We're reducing the contamination at the top of the contact. And we're doing, you know, we maybe are not able to create a situation where there's no tearing of the silicon rubber holding the column in place, but we've greatly reduced it, right? Which is how we get a long life out of these elastomers.
Mike, let me interrupt you here. We have a couple of questions, and I think that's a good moment to jump in. There's one question about the lifetime. What kind of lifetime can you achieve, and how does this compare to traditional Pogo pins?
Yeah. You know, I think Pogo pins are a very tricky one to gauge lifetime on, and we do Pogo sockets as well. Our general kind of discussion point around Pogo pins is trying to hit 100,000 cycles, right? In the auto test for GPUs, CPUs, those kind of environments, right? There's other pins for other package types that are probably capable of 1 million cycles. And if you care for Pogo pins, I think they do pretty well. But for these types with BGA devices, I think 100,000 is a really good level to talk about for Pogo pin life, right? Because even Pogo sockets require servicing and pin changes and cleaning. Okay, with the elastomer, we do have customers that will achieve 100,000 cycles on an elastomer. Traditionally, I don't recommend for the applications I'm usually discussing that we target 100,000 insertions. I think 50,000 insertions is a very healthy target that can be achieved, you know, over and over again, right? It still requires using the elastomer with some care, making sure it does go through cleaning. We can't brush an elastomer like you can Pogo pins, but we can go in between lots, blow debris out of the elastomer socket. These sockets are a little sticky to begin with. So if you have loose debris coming off of your devices from the substrate or the ball that's floating around in the socket, it's going to want to embed itself into the socket. So we usually recommend an air blow cleaning. And we also have some sticky tools that'll pull that debris out. But generally, 50,000 is a really good target on the elastomers.
Okay. Then some more questions about the material and the stack up. Can you say something about what kind of material you have, especially on the top side, and what kind of dielectric constant you have on this?
Yeah, I'll probably leave the dielectric and electrical stuff to the end, and maybe if we have time for some questions there. My team in Korea, they're really the experts on the electrical side. But as far as materials go, the powder is a gold-plated powder. We have a lot of different variations we do with the powder. There's plating thicknesses, gold recipes, right, for different applications. And most importantly, different sizes of powder, right? Depending on whether we're at a 1 millimeter pitch or all the way down to 0.2 millimeter pitch that we're doing for some customers now, right? So we have different techniques to create the powder and then process it correctly. And then for these different applications, even the ones on the screen, we have several variations of these that we pick depending on the customer's requirements. How much temperature is going to be involved, how much current, target C-res. There are always a handful of trade-offs as we pick the right elastomer. Okay, but for most of these, it comes down to the metal density. We do have different grades of silicon rubber for durometers, so we can change those as well. But with these newer elastomers, the key thing for these and making them last a long time is having room for the elastomer to expand, right? And that's what we're really working with successfully to get more life out of the elastomers. And then also you asked about the help with contamination. We do use kind of a layered approach in elastomers. So this top layer that's shown in black here, we can use a much higher density and harder silicon rubber at the top surface of the elastomer to give it more strength and more durability. Right? Okay, anything else?
And one question again to the reliability. Do you see that reliability is related to the pitch? So do you see a lower reliability, for example, if you have a tighter pitch?
Well, I think the elastomers themselves, can last, if we use that 50,000 insertion target as a real number, even as we go down to 0.4, we don't have a lot of automated tests at 0.2 yet, right? But we do at 0.4 and 0.3, 0.32. Those are very common pitches, especially in the memory world. And the reliability is still there. Probably the key thing to think about or to consider when we talk about how long the elastomer is going to last is how sensitive the testing is to a C-res change, right? So, if a brand new elastomer is starting at 25 milliohms, 30 milliohms per contact, the C-res will go up as it goes through its life, right? The idea is, it's not going to more than double inside that life cycle, right? So if we're at a 25 milliohm starting point with a brand new elastomer, when we get to 50,000, and our presentation here will show this, we should still be below 50 milliohms or in that range, right? Which is, for most of our customers, a very acceptable C-res range.
Can you, last question at this point, comment on the height of the elastomer and what it means for the compliance?
Yeah, I mentioned that earlier, but our elastomers are anywhere from probably 1/4 of a millimeter all the way up to 2 millimeters, right? And the 1/4 of a millimeter is not a very compliant elastomer. For any of these, we get about 30% compliance. So for a lot of our applications, the elastomer free height is right around 1 millimeter and with a stroke of about 0.25 to 0.35 millimeters, right? So about a 30% rule is what we do. And for the really large packages, today's CPUs and server processors, right, that might have warpage of up to 200 microns. We build our elastomers closer to 2 millimeters tall to compensate and give them the stroke necessary to work well through the life of the elastomer.
Okay. Thanks. Please continue.
All right. Okay, so some of these things we just covered, but one of the things that we deal with, daily as we work with some of our partners with their very, very large packages is warpage. So we have families of elastomers that can handle the 250 microns of warpage. We do testing, and we'll look at some of this where we thermal cycle the elastomers. We put them in a test position and run we do this inside a chamber or with a TCU head, where we'll drive the temperature from below freezing up to very high temperatures and back and forth. And what we do that for is to understand if the resistance is stable. If the temperature is going up, the resistance will go up, just like with a Pogo pin or probably any kind of contact technology. But what we want to see is the resistance come back down to the same starting point when the high temperature testing is over, right? Because this is the way our customers use the products. They, in a lot of cases, will socket apart and have it ramp up and down as it goes through its workload. So we do a lot of testing there. We'll look at that. We also have systems in our factory for doing cycling, of course, right? So that we can rapidly exercise a socket and look at the damage that's going to happen to that socket as it goes through, maybe up to 100,000 insertions. Okay, and then we do a lot of internal electrical modeling to help us fine-tune the elastomers for the high-speed requirements. Okay, this is looking at the warpage issue, right? So our traditional elastomer, again, single layer, little hard to see here, but this pressure paper was used to see how much engagement we're getting between the device and the contacts in that middle zone, right? With the warpage of the package and being a stiff substrate, we get a lot of pressure on the contacts around the perimeter of the package, but not nearly enough in the middle of the package. Normally ground and power, high density area in the middle. If we don't have good contact there, it's going to have higher C-res, and the potential for the elastomer to fail is much higher, right? So with our newer elastomers, again, we've put this air pocket and a stiffer top surface on the elastomer. We're getting, very uniform results with the pressure paper, right? So we're looking at how much force we're getting in the middle zones of a package versus the outer perimeter. And we want to see that as close as we can, right? Okay, these are some of the specs. And most importantly, this is, we're looking at resistance on a new elastomer and resistance on, a well-used elastomer, 100,000 cycles, right? So we're looking at how much change we're going to get. A standard elastomer, 45 milliohms per contact, up to 73 milliohms. That's pretty remarkable. It's holding very steady. Our newer elastomers, even better, right? We're down in the 25 to 30 milliohm per contact. These were done at 0.9 pitch, by the way. So 1 millimeter, 0.8, 0.65, all these specs are going to be pretty close. As we go down to 0.4, 0.3, the resistance numbers are going to be a little bit higher, maybe 10, 20% higher, just because of the smaller contact, right? Current carrying capability, because again, we've increased the density in the column as we do this. So we're up into the 4.5, 5 amps per contact, and that's continuous current carrying capability. Right. Okay, and then at the end, if we have some questions on the electrical, I'll let our team in Korea help with those. Okay, this is testing that we do inside a chamber, right? So we do this on for some of our partner companies that have very large programs, thousands of sockets. We build dedicated test PCBs that we can hook up to an automated resistance capture equipment. And we put this inside a thermal chamber, right? So we'll socket several devices, daisy chain devices, and we'll ramp the temperature up and down. In this case, -5 to 125 C. Okay, and one full cycle is 180 minutes, right? So The red would be our normal elastomer. This is our standard no air pocket kind of elastomer. And this is a very common trend, right? As we go through 100 thermal cycles, you can see the resistance is more than doubled. This is not from a lot of device insertion. This is just one device in one socket compressed one time. And as you ramp the temperature up and down, the metal particles are moving around in that contact. And with all the force pushing down, they can't pull themselves back into their normal position. So that's what causes this resistance to go up. You basically start losing metal density between the solder ball and the PCB, okay? With the newer elastomer, we're controlling that expansion, and we're allowing, with the air pocket, we're allowing that elastomer to kind of move a little more freely and able to maintain good density between the device and the PCB all the way through, right? So very stable on this. Okay, lifetime test. Again, this is some of the equipment we use. This is a C-res tester with a servo motor actuator. I think a lot of you have seen this or used this common piece of equipment in the industry. This is looking at how it presents the device into the socket. It has force control, and this is Kelvin connection to every contact on the PCB, every pad. So we're measuring the full array of devices as we use this cycler to do plunging, right? So a standard elastomer, you can see as it goes through 100,000 cycles, the resistance is trending up quite a bit. The standard deviation is very high on those standard elastomers. And when we move to our more advanced type, again, these are basically the same construction, just the XF is tuned for impedance. We're getting a much tighter grouping, low standard deviation per contact to contact within the array, and then also a lower resistance threshold. You know, it's still increasing, it's lower to begin with, and the amount of increase is dramatically reduced, okay? And this is talking about, oops, did I just go backwards here? Let me catch up here. Okay, this is just talking about some of the things we can do to improve the signal quality, right? We can tune the diameters of the elastomer. We actually have the ability to go in and tune the diameters in these different zones, right? So we can step this in different ways so that as it expands in this air pocket region, we can end up with an impedance, you know, I wouldn't call it an impedance match socket, but we can at least approach an impedance that works well for the overall signal path, device to PCB. And this is just the way we typically do our ANSYS analysis, looking at the signal and ground mapping, okay? And here's some S parameters on the 3 different types of elastomers, you know, going through this. Again, this is 0.9 pitch, so this elastomer is around 1 millimeter tall, and very, very high speed performance. You can see a half dB loss up into the 40 gigahertz range. And this is looking at the differential pair losses. Okay, just a big improvement when we go from standard to our optimized types. Okay, so just kind of in conclusion, the elastomers are becoming more of a workhorse for our customers because as the speeds go up and the pitches go down, the Pogo pin opportunities out there are more expensive, much longer lead time, and more difficult to implement into the test solution. And now we're reaching a point where an elastomer can be implemented easier, faster, at a lower cost of test than doing this with Pogo pins. Okay. There are any other questions, Mark?
Yeah, well, thanks for the presentation. There are a few more questions. So you mentioned the top layer of your new elastomer was always kind of a harder material. So does this require then more force to really have the same kind of compression?
No, what we do, the main point from of this type of elastomer is moving the stroke area of the elastomer down internal to the elastomer. So in this cross section, this black zone, right, this is where we would have a higher density of metal. So as the ball engages this surface, or in the case of an LGA or QFN, we actually grow the metal column above this upper layer. So there'd be a little bump sticking up proud towards the device. But we're moving the stroke area of the elastomer, we're moving into the body of the elastomer. So around here, the metal particles are still embedded in silicon rubber, but there's an air pocket surrounding each contact. So as it squeezes down, this is where the majority of the stroke for the elastomer happens, right? It's internal, it's controlled. The thin layer of silicon rubber surrounding all those metal particles doesn't tear. It flexes, but it pulls back. And we're not getting a lot of movement at the top surface. So that density gives us the longer life. And the force is virtually the same.
Mm-hmm. And then another interesting question, you were talking about this air cavity. Is there any risk that some of the gold basically finds its way into this air cavity and makes a short between the two columns?
No, there's still silicon rubber. It's a little tough to look at. Maybe this image, this electron microscope image is the best one, but this is looking at the top surface, but it's representative of how the elastomer is made. It's not metal powder with just a layer of silicon rubber on the outside, right? It's silicon rubber between all of these little particles of metal, right? So these gold-plated particles, they squeeze together as you apply stroke or force onto the top of the contact, but there's silicon rubber throughout this entire contact column. So the metal really won't tear itself loose and move around inside, right? But we've never seen that happen. On the older or the standard type elastomers, right, the metal still would not migrate. This would be silicon rubber between the contacts. The metal would never migrate between the two, but you could see evidence here on damage where little parts of the metal maybe have fallen off or broken free from the contact pad at the device engagement surface with the BGA ball, right? With the newer elastomers, that's minimized because this top area is bound in a much firmer way, right? It's higher density, stronger silicon rubber. It's almost strong enough you could wire brush it. We wouldn't recommend that, but it's almost that strong.
Okay. What is the material used to house the elastomers, and can you do cutouts on the top side to accommodate components on the bottom of the DUT?
Yeah, it's a great question. This type of elastomer we are building. Let me go back to this slide. These are not exactly matched here. In this slide, this cross section, there's two air pockets, right? So what we're really looking at in this one is one of our taller constructions for a CPU type device. And we very commonly will cut a void down halfway through. And in some cases, we go all the way through the elastomer where we have room for those decoupling caps that are on the bottom surface inside the array of the device. So we can easily accommodate that. And we can make this elastomer, this is a layered elastomer, right? This one's probably 2 millimeters tall. So we would have the ability to deal with a component that's 1.5 millimeters very safely.
Hmm. And the material for the housing of the elastomer?
Oh, I'm sorry. Yeah. So the elastomer is bonded onto a substrate, basically. This would be FR4 for most of our applications. So we grow the elastomer molded onto a rigid frame. In some cases, very, very fine pitch, we use stainless steel, and we don't have frame material between the contacts. There's only frame material around the perimeter of the array. But for most packages, 0.4 millimeters or greater pitch, this bottom FR4 frame is drilled for each contact. And then that is what registers it to the PCB and to the device housing, right? That would give guidance to the device being inserted. So you make sure the balls are going to line up with the contacts or pads to the contact. And then we do have another area that's not shown in this presentation, but this film on the top surface, we commonly add a second film that is what we call a ball guide film for BGA. So every ball drops into a hole to do the precision alignment of each solder ball to the contact. So FR4 for this bottom piece.
Okay. Well, thank you very much. There are a couple of more questions, but we're running out of time. So I think all the questions are still open and you may want to address to Mike directly. Thank you very much for this very interesting presentation.
In conclusion, I'd like to very much appreciate our sponsors who've made this event possible and allowed us to do this without registration charge. Our premier sponsor is Kohu. Our emeritus sponsor is JonsTech. Our honored sponsors are ISC, iWin, and TSC. Our distinguished sponsors are Backer Hot Watt, Innovative Circuit Engineering, JMT, Nidec SVTCL, R&D Altanova, and UI Green. Our exhibitors sponsors are ELES, MJC, Phoenix Test Arrays, and Smiths Interconnect. So thank them once again, and when you have an opportunity, please thank them. An extra special thank you to Kohu, our premier sponsor, the market leader in test interface solutions for the most challenging applications. Our honored sponsor, ISC, global #1 total test solution provider. And iWin, the test probes provider for high signal integrity at extremely high speed test. And once again, I would thank all of you for attending and participating in this week. Look forward to seeing you all online the week of October 25th for TestConX China, and then March 3rd through 9, 2022 for our in-person event in Mesa, Arizona. So I wish everybody a good rest of your day. Thank you for your participation.